Hi, welcome to the second video of proving why root 2 is irrational. I highly recommend watching the first video. If you haven't seen it, you can click the screen now and it will take you to a new window, or you can click the link in the description box down below. So, now for the second part. We're going to be proving this by proof by contradiction as well. If you remember what that is, you pretty much assume the opposite to what you want to prove. So we're going to start by assuming that root 2 is rational. So that means that we can express root 2 as a fraction that's p divided by q, where p and q are both integers. So with a bit of quick rearrangement, we square both sides to get rid of the root 2, we end up with this equation, 2q squared equals p squared. So if we split the 2q squared up into q squared plus q squared, which equals p squared, we get the sum of two squared numbers equaling a third square number. I don't know about you, but this kind of reminds me of Pythagoras' theorem. And apparently I've been spelling Pythagoras wrong my whole life. Anyway, Pythagoras' theorem states that a squared plus b squared equals c squared, where a and b are the sides of a right-angled triangle and c is the hypotenuse. Now with the equation that we have, q squared plus q squared equals p squared, we actually have a right-angled triangle with sides q and hypotenuse p. So if we want to show that root 2 is really irrational, we just have to prove that this triangle isn't possible when p and q are both integers. Let's start by drawing a right-angled triangle with two sides having side length q and the third side having side length p. Yeah, my hand kind of bumped my camera tripod, so I have this random line coming into my triangle. Okay, so I'm going to go ahead and label our triangle ABC, and I'm going to put in another point, D, such that the length of CD equals Q, and since the length of the whole AC equals P, then the length of AD just equals P minus Q. And now we have BC equals CD, so BC equals CD. I'm going to draw another point E, such that line ED is perpendicular to AC. Since the two sides of our big right-angled triangle are equal, and we have a right angle in our triangle, we know that the other two angles in our triangle are both 45 degrees, because the three angles in the triangle must add to 180 degrees. Now looking at our smaller right-angled triangle, our third angle must equal 45 degrees as well because the three angles in the triangle add to 180 degrees. That means that triangle ADE is actually an isosceles triangle, meaning that we can find the length of DE, which must also be P minus Q. You can also figure out that EB equals P minus Q as well by seeing this yellow line of symmetry I'm drawing down the diagram. But I prefer to find my side lengths in a messier way. So let's try and find the length of AE. Maybe you've already noticed that triangle DAE, that's this small right-angled triangle, is similar to our big right-angled triangle BAC because they both have exactly the same angles. It's like you've taken your small right-angled triangle and you've flipped it and made it bigger to get the big right-angled triangle. We can exploit this similarity by writing a new equation about the ratios of the two triangles. So AE, which is the hypotenuse of the small triangle, divided by AC, which is the hypotenuse of the big triangle, that equals P, has to equal DE, so one of the sides of the small triangle, which equals P minus Q, divided by BC, which is one of the sides of the big triangle and equals Q. So if you rearrange everything, you get AE equals P squared over Q minus P. From what we did before, we found out that 2Q squared equals P squared. So if we substitute this back into what we have, AE just equals 2Q squared over Q minus P, which equals 2Q minus P. So let's look at triangle ADE, the small right-angled triangle. And let's redraw it. So we have two sides which are P minus Q, and our hypotenuse equals 2Q minus P, so we just calculated that. But what do you notice about this triangle? I mean, 2Q minus P is an integer because P and Q are both integers, and p minus q is also an integer. So it's like we've given birth to a new triangle that has integer side lengths. Now you're asking me, Natalia, can't we just do that again? Draw another perpendicular line, get an integer side length triangle, and then just keep on drawing lines. And you're right, every single triangle that you get has integer side lengths, which is impossible because you can keep on repeating this process infinitely many times and still get a triangle with integer side lengths. And yeah, that's kinda not possible. So, what have we done here? Have we disproved anything? We kind of have, right? Because we assumed that root 2 is rational. That turns out that it's wrong because we got this weird infinite triangle integer side length thing, which means that square root 2 is actually irrational. That's the end of this video. Thanks for watching! If you want to see our last video, the part 1 video of proving why root 2 is irrational, there's a link in the description box down below, as well as a link to our Introduction to Circular Geometry part 1 video. If you want to see our email address, this is it, feel free to email us, and our website address, which is this, and feel free to visit it anytime you want. A really big shout out to everyone doing the International Mathematical Olympiad this week. I hope you have so much fun doing heaps and heaps of maths, and I'm really jealous of you. But yeah, good luck!